Hi, pattern matchers. So we have seen one way to bring together data types and category theory through, first of all, the category of algebras, and secondly, to not just ask for any old algebra, but to ask for an initial algebra. And we saw that this corresponds to pattern matching in the sense that if you have pattern matching, you can get an initial algebra. But now I want to show you something which I think is very cool, which is that you can also go the other way. If you have an initial algebra, then you can actually get pattern matching. And you might say, what's the big deal? And I will tell you that the big deal is not just pattern matching, but dependent pattern matching. So the fact that we can pattern match and get something of this type, right, where we actually have something which depends on this. This is also called induction, right? So we can do induction, and uniqueness is going to be really important for this. So let me show you how this works. So remember, this was the definition of what it means for an algebra to be initial. So it means that we have an algebra like this, and for every other algebra, there is a unique morphism to it, right? And so that the point here is that that makes it really easy to get pattern matching of the form n to a, for example, right? But it doesn't a priori give you a dependent function, because this fold here is just an ordinary non-dependent function, right? So the trick, which is a clever trick, which has been known for quite a long time, is so the only way we can get functions out of our initial algebra here is to make another algebra, right? So if we have some property p, let's just do this for the natural numbers, even though this works exactly the same for any algebra. But if we have some property p, and we know p of 0, and we know for all x, p of x implies p of suck x. So if you have a p0 like this, a ps like this, then we would like to conclude that for all n in n, p of n, right? Right, so what we do is we try to make an algebra on the set sigma n p. So this is the collection of all the pairs of some n and some proof that p of n holds for this n, right? So let's see if we can do this. So what we need is something of this form, right? Where f is this functor for the natural numbers in particular. And if we have that, then the initiality property is going to get us a map into this thing, right? Which is a good start. So let's see if we can do this in Agda. So here I have all the pieces. So I'm trying to prove induction, and I'm not going to do any pattern matching or any recursion. I'm just going to use the fact that the natural numbers is initial. So I have a p, I have p of 0, I have a step case, and I want to prove for all n p of n. And let's ignore most of it first. So right now, we're just trying to construct this other constructor for the sigma type, right? So here I'm going to do pattern matching on the x, because that comes from this functor. That's not doing pattern matching on the natural numbers, which would be cheating. But I am pattern matching on the x. I know, as usual, that I have two real cases here, right? It's either the thing representing 0, in which case I don't care about this, or it's the thing representing the successor. So in this case, I have to give something back in sigma n and p, and because I want this to be 0, so this is a pair of two things, and here I'm going to use the 0 in the first component for the n, and I'm going to use the proof I have of p of 0. And similarly here, what do I have? So my x here is a recursive, represents a recursive call, so it's already of the form n pn. Where n is a natural number, it's a bit hard to see. Pn proves p of n. Right. And I have to give back a pair of things. So in the first component, I'm going to use the successor. And in the second component, I have this ps, which if I give it an n, the proof of p of n, which I have. Okay, so I managed to assemble the pieces of this thing from the pieces I had, these things. So now if you go back here, that means that I have this con star like this, right? So that means that I get a function from n, this was f of this, f of n, the con, so I get the fold going this way. F of fold. But the problem is that, so that says that for every n here, I will get a pair of an n and a proof of p of n. But a priori, I could just get the pair 0, p0 all the time, right? I don't know that the n I get here necessarily is related to the n I put in. So this is where uniqueness comes in, because now I can, this is the clever trick, I can look at the first projection here. Which takes me back down to n. And then I can show that this first projection also is an algebra morphism, which means that this diagram commutes. Right. And then by uniqueness, I know that there is exactly one algebra morphism from here to here. But now I have two candidates. I have this one, because the composition of two algebra morphisms is an algebra morphism. That's a fun exercise. But I also have the identity, because the identity also makes this commute, right? So what does this say? It says that if I first do the constructor and then the identity, that should be the same thing as if I first do f of the ID, which is the same as just the identity, and then do the constructor, right? So since I have two algebra morphisms here, they must be equal, and that means that if I now take first this one and then take the second projection, then normally what I would get, so if I do fold con star followed by the second projection, then normally that would go from n into p of the first projection of the same thing. But now I know that this first projection is equal to the identity, like this. So this whole thing is just p of n, which is exactly what I wanted, right? So I used the fact that there exists something to get something into the sigma type, and then I used uniqueness to see that it really gave me the proof that I wanted, right? So if we go back to Agda, we can see this happening here, right? So here some p is the thing I get from the fold, which gives me some p of n for every n, and then first is untouched, is the proof that the first projection really leaves the n untouched, right? And then we can use that proof to fix up the type of the second projection. And we see that this is unique by just filling in a few more steps, right? So the first one we have to see here is that the first projection is an algebra, so that's what we needed to see that this diagram down here commuted. And so let's just do that. And then here finally we needed to see that the identity was an algebra, but that let's see. Oh, that's not here. But that just follows from the fact that it preserves identities, right? So all we need to know is we need to show this little equation, but we see in both cases this is actually really easy. So it follows easily. So this is really cool, right? From what looked like just non-dependent pattern matching, we managed to get real dependent pattern matching induction by making essential use of the uniqueness of the fold, right? And there's nothing special about the natural numbers for this. You can do this for any data type. I think this is really cool.